Okay, let's talk about metric spaces. I briefly mentioned metric spaces in the triangle inequality video, and we're going to use some things from that video, so you might want to refresh yourself and watch that again in this video here. So the metric space is a set of points or a set of elements that we can measure the distance between. And so I need a set, I need some things that I measure the distance between, and then I also have to tell you how to measure them. So together they form a metric space. So our definition for metric space, a metric space is a set of points, say x. This could be the real numbers, it could be complex numbers, it could be functions, it could be a set of all polynomials. We can measure the distance between two polynomials if we write down the right measurement. There's ways to do that. It could be differentiable functions. This could be almost anything, and we've been trying to decide how to say two things are close to each other. Well, we can say two functions are close to each other if their graphs are close to each other, or maybe all of their derivatives are about the same, or things like that. But for now, we're just going to be worried about the real numbers, but we're going to set up this sort of general notion so that we can do that later in the course. So it's a set of points and a function, we'll call it d, that takes two values from x, so x2 or x squared, and it sends them to a real number, which is how far apart those 2 points are, such that d has the following three things. Well, the first thing d needs to satisfy is that it's positive, right? If it's going to measure a distance, it should be a positive number. The distance between two things doesn't make sense to be negative. It should also identify points in the sense that the distance between a point and the exact same point should always be 0. So I need d of p comma q is bigger than 0 if p is not equal to q, and d of p is equal to 0 if I measure the distance from p to itself. So I would call this so positive identifying. So our metric is positive and identifying. It's also good that if I have a distance from p to q, it should be the same thing as the distance from q to p. Right? So this is symmetric. Okay. And then the last thing that we need is why I mentioned the triangle inequality video earlier. The distance from p to q should be, the straight line distance should be smaller than if I went through another point. So distance from p to r plus the distance from r to q. So to get from p to q, if I go sort of straight line distance, that should be shorter than if I have to go through r, the distance from p to r and then from r to q. Okay, that's the triangle inequality. Okay, so now that we have our definition for a metric space, or what it should mean for us to measure something, let's come up with some examples here. Okay. Our first example is just going to be the real numbers. And the metric is going to be the absolute value. So, reals with absolute value. Okay. Let's see. Does this satisfy it? So, what do I mean by absolute value? Well, let's write down that first. So, d of x, y should be the absolute value of x minus y, right? The absolute value by itself just takes a real number, but I need something that takes in two real numbers and sends out a real number. So it takes two real numbers, it gives me a distance. This is going to be my metric. Does it satisfy A? So absolute value of x minus y is bigger than 0. That checks out. And the absolute value of x minus x equals 0, right? That also checks out. So it is positive when x and y are not 0. And it's exactly 0 when I have x and itself. Okay, good. So let's see, does it satisfy symmetry? X minus y, well, that's equal to absolute value of negative x minus y, which is equal to absolute value of y minus x, so symmetry checks out. And C, we've already seen that this should work for the triangle inequality, but I've got my triangle inequality was just straight absolute values. I had the absolute value of a plus b, not a minus b. So we have a little bit of work to do, but not too much. So let's look at the absolute value of x minus y. Okay, and I need to introduce a third point. That is equal to the absolute value of x minus r plus r minus y, right? Okay, so I've introduced this point r, which is kind of the third point on the triangle, going from x to y. I'm going to have to go through r. So I haven't actually added anything. This is equal to 0, so I have equality here. But now I can use the triangle inequality on these two pieces. The two pieces I'm going to use the triangle inequality on are this piece and this piece, right? I've got the absolute value of the sum of two things, so now I've got that plus sign. I can actually say then that this is less than or equal to the absolute value of x minus r plus the absolute value of r minus y. Right. And that is exactly what we needed to show. The distance from x to y is less than or equal to the distance from x to r plus the distance from r to y. So there's our triangle inequality, and it checks out. We just had to introduce that plus and minus r inside the absolute value for it to work out for us. Okay, so there's our first basic example of a metric space. Let's see another example. Let's look at R2 with the Euclidean metric, our standard way to measure the distance between 2 points in R2, which is the square root of x1 minus x2 squared plus y1 minus y2 squared, right? This is kind of our standard, our very basic notion of distance in any algebra class that you probably taught in high school. And this is a very natural thing to start with. And so let's show that this is a metric. So we need positivity, and this is positive because square root of x1 minus x2 squared plus y1 minus y2 squared is bigger than 0 as long as this isn't 0 and this is 0, not 0. Not 0 or that's not 0. As long as one of those two things is not 0, I'm taking the square root of a positive number. Square root of a positive number would be positive. So long as not both x1 equals x2 and y1 equals y2. So as long as one of the components is different, we're positive. And if both components are exactly the same, I've got the same point, and we have the identifying part of A as well. Okay. Do we have symmetry? Yeah, we've got symmetry. Square root of x1 minus x2 squared plus y1 minus y2 squared is exactly equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Right? If I put them in the other order, it doesn't change anything, so that checks out. The triangle inequality with this is a little trickier. When we use the Cauchy-Schwarz inequality, which I think I had you prove, or at least look at the proof for, that's where this comes in. Let's see. So the square root of x squared, x2 minus x1 squared plus y2 minus y1 squared. That has to be less than or equal to the square root of x2 minus x1 squared, no, x x1 minus x3. We need that third point, plus y1 minus y3 squared plus the square root of x3 minus x2 squared plus y3 minus y2 squared. Okay, this comes from the Cauchy-Schwarz inequality. It's a bit technical for this video. Your book does a okay job, and there's a lot of other videos online that do a better job than the book of explaining this. But that is true. I'm going to give you a different metric on R2, and we'll prove the triangle inequality on that different metric just for another example of dealing with metric spaces. And that one's a little more straightforward to prove, and we don't have to get so many technical details. We can use what we've already proven with the absolute values to do that. So let's look at R2 with the taxicab metric. I think I briefly mentioned this in another video as well. So let's put things together here. Let's grid this up a little bit and take a couple points. Let's take a point here. And let's take a point here. So straight line distance, if I call this x and I call this y, The straight line distance would be the metric that we had just used. The taxicab metric says, well, if these were the streets in a city, how far would it take, or how many blocks would a taxicab have to go to get from X to Y? Not as the crow flies, but as the taxi drives. So I've got to go 4 this way and 2 this way. So our distance from X to Y using the taxicab metric is going to be 6. So let's write down an equation on how I would have to do that. So the first thing I would have to do is figure out how far in the x direction we would have to go. So this is going to be x2 minus y2. So the second coordinates of both of those. I guess these would be the first coordinates, wouldn't they? x1 minus y1. And let's get that line back. Okay. And then the second coordinates would be x2 minus y2. And these should be absolute values because I want the x distance to be positive and the y distance to be positive. And then I'm going to have to add them together. So the distance from, say, x1, x2 to y1, y2, if I've got 2 different points there, first coordinates, second coordinates, it's going to be the absolute value of x2, x1 minus y1 plus the absolute value of x2 minus y2. Okay, a lot of you are probably throwing your hands up and yelling at me for changing notation here. This notation is better for us in the long run because it allows us to generalize to higher dimensional spaces. If I just had x's and y's, that's fine. I can have the first coordinate always be x and the second coordinate always be y. If I go 3 coordinates, I can go x, y, z. But what if I wanted to go to 5-dimensional space? Then I'd have to have the first component and the second component and the third component and the fourth component and the fifth component, and I've run out of letters by the time I get to 3. That's kind of why we started x, y, and z. Most stuff is only in the elementary and secondary grades, just 1-dimensional up to 3-dimensional. But we do want to make this general so we can go to higher dimensions. Okay. And this does generalize. I take the difference of the first components, I take the difference of the second components, I take the difference of the third components, absolute value each of the differences, and add them together. I get a taxicab metric on higher spaces. But what I want to do is I want to show that this metric is an actual metric. So let's start with R2 and the taxicab metric is a metric space. So the first thing we have to show is we have to show positive and identifying. So let's take 2 points, x and y. So the distance from x1, x2 to y1, y2 is equal to the absolute value of x2 minus x1, x1 minus y1. I'm even confusing myself on this notation. But I want to take the difference of the first component plus the difference of the second component. Okay. And this is greater than 0, just like we had said above, as long as both x1 or x1 is not equal to y1 and x2 is not equal to y2, as long as both aren't equal. If they are equal, we have identifying. Otherwise, get equal to 0. So this does check out for us. B, we need symmetry, and symmetry is fairly obvious here again. D of x1, x2, and y1, y2 is equal to the distance from y1, y2 and x1, x2. And that's just because it doesn't matter which order we put things in here, right? So I can swap these just because the absolute value lets us swap those. That one checks out. The one that actually has a little bit of work to do is the triangle inequality. So let's go with the distance from A1, A2. So I'm going to take 3 points to B1, B2. I need to show that that's less than if I go through a third point, C. Okay, so let's start with this. This is equal to absolute value of A1 minus B1 plus A2 minus B2. If I was going to go through a third point, when we showed the absolute value inequality above, we introduced a middle variable, that middle point. We're going to do that again in 2 spots this time. I get A1 minus C1 plus C1 and then minus B1. So I've introduced 0 in sort of a weird way here. And we're going to have to do that in the second component as well. A2 minus C2 plus C2 minus B2. Okay, so we've introduced our middle point in 2 different ways, and then we get to play that same game as above. This is less than or equal to, well, if I split up the absolute value, the triangle inequality on just the absolute value parts, A1 minus C1 plus C1 minus B1 in absolute value, both of those, and then break it up over here as well. A2 minus C2 in absolute value plus C2 minus B2 in absolute value. And this now, if I take these guys together, that's the difference between A and C. Lots of parentheses. Plus the other stuff, the leftover stuff, is the distance from C to B. Okay. So our triangle inequality works out. As an exercise for you guys, I'm going to have you try and do this in higher dimensions, say n-dimensional space. And it's straightforward. We use the same trick and do it just n times instead of 2 times. It gets a little messy with some notation, but it'll be good practice for you introducing those variables, those adding to zeros.